Dear students, in the previous class, we found the Bessel function. We discussed about what is the Bessel equation and the Bessel function. And we know that Bessel function, that is Jpx equals sigma n ranges from 0 to infinity minus 1 to the power n x by 2 all to the power 2n plus p all divided by n factorial into p plus n factorial, which is known as Bessel function, Bessel equation and the Bessel function. Okay, now this Bessel function, here we find this Bessel function for the exponent m equals p. So we find out the initial equation, then there are two values for this exponent, that is m equals plus or minus p. So this jpx is for m equals p itself. Now it is in order to find out the general solution of the Bessel equation, we have to find out a solution which is not a constant multiple of this jpx. Our next task is, or our aim is, find out the general solution of this Bessel equation. So in order to find out the general solution, we have to find another solution which is not a constant multiple of this jpx, and that solution, if that solution exists, that solution is said to be Bessel function of second kind. This is a Bessel function of order p of first kind, and now we have to find out the another solution which is not a constant multiple of this jpx, and which is known as, if that solution exists, which is known as Bessel function of second kind. Okay, so for in previous class we discussed about the two values of this m, and we know that m has two values, m equals p, and m has another value, m equals minus p. So when m equals minus p, then as usual we know that x square y2 prime plus xy prime plus x square minus p square into y equals 0 be the Bessel equation, and we assume let y equals sigma n ranges from 0 to infinity an x to the power m plus n be the required solution. So as we can find out this y2 prime, y prime and y2 prime, and substituting all of this value in this equation by putting this m equals minus p, then and negating the coefficient of x power m plus n to 0, you have this relation, that is recurrence relation a minus 2, you have this recurrence relation. Like the previous case, it is a n equals, here it is minus a n minus 2 divided by n factorial into a n minus 2. So a n equals a n minus 2 into n minus p, not n factorial. So the recurrence relation in previous case, when m equals p, our recurrence relation is a n equals minus a n minus 2 by n into n plus p. But if you substitute the value or gives the exponent m is minus p, then you have this recurrence relation a n equals minus a n minus 2 by n into n minus p. Okay, so clearly we know we have a0 differs from 0, and a1, what is a1 here? A1 is again 0. Why? Because if you put n equals 1, minus a1 is here a minus 1. When n equals 1, it is a minus 1, which is not defined. So a1 equals 0. And when n equals 2, what is a2? a2 equals minus a0 by, when n equals 2, it is 2 into 2 minus p. 2 into 2 minus p. And so a2 equals minus a0 by 2 into, when it is n minus 2p, not n minus p, it is n minus 2p. The recurrence relation is in this way, an equals minus a n minus 2 by n into n minus 2p, not n minus p. It is n into n minus 2p. So it is minus a0 by, it is 2 minus 2p. So means, what is a2? It is a2 equals minus a0 by 2 square into 1 minus p. And 2 goes outside. Similarly, you can find out this. Again, you can see that a3 equals 0. Why? Because a3 is in terms of a1. But we know that a1 equals 0. So a3 equals 0. And again, you can find out a4. That is again in terms of a0. In terms of a0. Surely, we can see that a5 equals 0 and so on. So, the values of a is when I is odd, when a has odd suffixes, all of these values should be 0. That is a1, a3, a5, etc. are zeros, and a2, a4, a6, and means the a has even suffixes are defined in terms of a0. Okay. So after supplying this value or this values of a0, a1, a2, a3, etc. in y, we know that y equals it is sigma n ranges from 0 to infinity. It is an x to the power n minus p. Why? Because m is minus p. So this is nothing but it is x to the power minus p into x to the power minus p into, what's the means here? First time is when n equals 0, it is a0. So a0, and when n equals 1, a1 is 0. When n equals 2, it is a2, that is minus a0 by 2 square into 1 minus p into, yes, it is x square when n equals 2 plus etc. Okay, so that means this y equals, it is a0 into, here a0 is common, take outside, so it is a0 into x to the power minus p and into sigma n ranges from 0 to infinity. Finally, it is minus 1 power n. It is x to the power 2n all divided by 2 to the power 2n, 2 to the power 2n into n factorial into n minus p factorial. Okay, or 2 to the power n into, sorry, not n factorial, it is simply 2 to the power 2n into n factorial into, okay, there is a product, that is 1 minus p, 2 minus p, 1 minus p, etc., 2 minus p, etc. into n minus p. Okay, after substituting all these values, means a0, a2, or a2, a4, a6, etc., all the other values are zeros, then we have y equals x to the power minus p into this one. That can be rearranged as in this way. That can be expressed as in this way. That is, when m equals minus p, y equals a0 into x to the power minus p, sigma n ranges from 0 to infinity, minus 1 power n, x power 2n, all by 2 power 2n, n factorial, 1 minus p into etc. into n minus p. So, since we know that a0 is differs from 0, so you can substitute the value of a0. Here put a0 equals, in previous case, what is a0? a0 is 1 by 2 power p factorial. Here you can replace this way, a0 is 1 by 2 power minus p into p factorial. If you substitute that value of a0 here, so what is y? Y equals then it is a0 means it is 1 by 2 power minus p into p factorial into x to the power minus p, that is sigma n ranges from 0 to infinity, minus 1 power n, here x to the power 2n minus p, all divided by 2 to the power 2n, n factorial into 1 minus p into etc. into n minus p. Enough. So, which is nothing but you can again rearrange it as y equals sigma or y of x, sigma n ranges from 0 to infinity, it is minus 1 to the power n. There is on denominator, there is 2 power 2n, and here 2 power minus p, again it goes to inside of the summation, so you have x by 2 all to the power 2n minus p, 2 power 2n minus p, and x power 2n minus p, that can be rearranged as x by 2 all to the power 2n minus p all divided by n factorial into, there is a p factorial, and after that 1 minus p, 2 minus p, etc. n minus p, so it is n factorial into n minus p factorial. So you can see that this y of x equals sigma n ranges from 0 to infinity minus 1 power n x by 2 all power 2n minus p by n factorial n minus p factorial. This can be rewrite as j minus p of x. So this is called the Bessel function. This is called a Bessel function of second kind. Bessel function of second kind, that is j minus p of x. J p of x is Bessel function of first kind, and j minus p of x is said to be Bessel function of second kind. Now, is there any relation between, or is one of them is a constant multiple of other? That's our next task. So here we know that jpx. What is jpx? Jpx is this one. And what is j minus px? J minus px equals, again we write, it is sigma n ranges from 0 to infinity minus 1 power n x by 2 all power 2n minus p all divided by n factorial into n minus p factorial. This is j minus px, Bessel function of second kind. So in 1, this is 1 and 2. So in 1, when n equals 0, means what is the first term there? When n equals 0, the first term is it is x by 2 all power p divided by it is p factorial. Okay, so surely this is bounded near x equals 0. So the first term of jpx is x by 2 all power p by p factorial, which is bounded near x equals 0. And 2, in equation 2, when n equals 0, what is the first term? The first term in equation 2 is, it is x by 2 all power minus p divided by minus p factorial. X by 2 all power minus p, that is 1 by minus p factorial into 1 by x by 2 all power p. Clearly, it is unbounded near x equals 0. So the first term of jpx is bounded near x equals 0. The first term of j minus px is unbounded near x equals 0. That means that jpx is finite at x equals 0. So at x equals 0, this means at x equals 0, jpx, the Bessel function of first kind, jpx is finite, and at x equals 0, j minus p of x is infinite. So these are the two important things. That is, at x equals 0, jpx is finite, but at x equals 0, j minus px is infinite. So clearly, one is not a constant multiple of other. Why? Because one is finite, other is infinite. So clearly, one is not a constant multiple of other, means jpx and j minus px are linearly independent. So jpx and j minus px are linearly independent. Thus, the general solution of the Bessel equation is, that can be rewritten as the, or the general solution can be expressed as the linear combination of these two linear independent solutions. That is, y of x equals, it is c1 jpx plus c2 j minus px, where c1 and c2 are any two constants. So this is the general solution of Bessel equation, that is y of x equals c1 jpx plus c2 j minus px, which is known as the general solution of the Bessel equation, x square y2 prime plus xy prime plus x square minus p square y equals 0. This happens why? Because this jp and j minus p are linearly independent. Why? Because of these characters. Jp is finite when near x equals 0, and j minus p is infinite, so they are linearly independent. They are the solutions. So the general solution can be expressed as the linear combination of these two linearly independent solutions that can be expressed as in this way. That is y of x is c1 jpx plus c2 j minus px. Agreed.